Okay, we'll now move on to exercise 1.4.2 from the book. Let me just say, in case some of you find difficult to show the square root 3 over 2 is irrational, that the same argument here works if instead you use s the square root of 3 and t the square root of 2. Then the product will do the square root of 6. Yeah, the square root of 6. And the proof that this is actually rational is simpler. Okay, so this is it's more similar to the proof for the square root 2, square root 3 for irrationality. Okay, now let's move on to exercise 1.4.2, which is kind of a short thing, but this is something that I'm very inclined to ask of you during the exam, second midterm perhaps. So how does this go? This requires you understand the concept of supremum very well and the characterization that we gave not long ago. Let A be a subset of R, be non-empty. Very important. Non-empty and bounded. Bounded above. And let S be in R, be a number in R, with the property that for all n in n, s plus 1 over n is an upper bound for A, while s minus 1 over n is not an upper bound for A. Show that S is then the supremum of the set A. Okay, so this is a kind of problem that may look, for some of you, may look a bit intimidating at first when you didn't have experience with dealing with this kind of problems, like showing that something is a supremum of a set. But if you really know that the only two things that you can use to show that something is supremum are either the definition, meaning that something is an upper bound and is the least of all upper bounds, or the characterization of supremum, meaning that you're given an upper bound and you have to show that if you subtract anything from that upper bound, then you find an element in the set, then that is the supremum. If you subtract anything from that, then you subtract anything from that from that upper bound, and you find an element in the set that is slightly bigger than that or bigger than that, then you have your supremum. So that's the characterization of the supremum. if whenever you're asked to show that something is supreme, you either have to show use this property or this characterization or the definition. And when you know that, and you see something like this, it tells you it's probably good to use the characterization because you're subtracting something from the thing you want to show that is the supreme. So that means S. So you should think of 1 over epsilon as being your, or no, 1 over n as being your epsilon. So how do you show this? So okay, I mean, maybe we'll need to cut this short because I'm running out of batteries and I don't have the cable here, but we'll continue then in the next video. I mean, if for some reason I'm not able to finish. But let's start by showing. So the first step, first we show S is an upper bound. Why is this true? If it were not, we would be able to find some A in A, some element A in A, such that A is bigger than S. This means actually A minus S is positive. So this actually implies A minus S is positive. So by the Archimedean property, this implies then that there exists some n in n such that A minus n is bigger than 1 over n. A minus S, I'm sorry. A minus S is bigger than 1 over n. But then, this implies here that A is bigger than S plus 1 over n. So, this is not an upper bound. It's not an upper bound. So this is impossible. Okay, because we said that S was an upper bound. I mean, that for every n, S plus 1 over n was an upper bound for the set. But we found an element in the set that is bigger than S plus 1 over n, so that means that S is not an upper bound. So that's a contradiction, or if you want to phrase it, it's a contrapositive. So if we didn't know that S plus 1 over n, we're not assuming that S plus 1 over n is an upper bound, then we conclude that there's an element that is bigger than S, then S plus 1 over n cannot be an upper bound. So you're showing a contrapositive here. There exists one n. So the contrapositive, remember P implies Q. Now you're showing not Q implies not P. What is not P? What is P is for every n, S plus 1 over n is an upper bound. The negation of that is there exists an n such that S plus 1 over n is not an upper bound. This is what we're showing here. Okay, so that shows that S is an upper bound. So the next step is to show that is the least upper bound. For that, we'll use the characterization.